Hi everyone, I'm Alex Moehring. I'm an assistant professor at Purdue. This is a project joint with Nikhil Agarwal and Alex Litsky at MIT. It's called Designing Human-AI Collaboration, a Sufficient Statistic Approach. So thank you to the folks at Wharton for including me on the program. So let's dive on in. So I think a lot of us are here in this room because we're interested in how AI tools are going to impact human decision makers. So questions like, do human-AI collaborations improve the performance over either modality alone? Do humans effectively use AI tools? And ultimately, how should we design the provision of AI tools to humans to maximize the performance of the collaborative team? And this sort of last question is what we're going to try and tackle today. I should say at the outset, this is going to be a project studying human-AI collaboration and classification problems. So this is not a project about LLMs or generative AI, just to set expectations. But in particular, we're going to consider a design space where we allow a designer to, as a function of the AI assessment, they can just decide whether or not they want to fully automate the case, and follow the recommendation implied by the AI tool, or they can delegate the task to a human decision maker. If they delegate the task to the human, they get to choose what, if anything, they want to reveal to the human decision maker about the AI's assessment. So we're going to call this a disclosure policy. It's important to note that the space of policies here is quite large. So in this paper, we're going to introduce what we call a sufficient statistic framework, where we are able to tractably solve this optimization problem. So we're going to apply this empirically in a human-AI collaboration task where humans are assessing the veracity of facts. So we're going to have a two-stage experiment. In stage one, we're going to estimate the sufficient statistics that's required to design optimal policy. This is going to turn out just to be the performance or the probability of a correct classification by a human decision maker, conditional on the AI assessment that they observe. And I'll tell you a little bit more about how we use that to predict performance in a little bit. Once we estimate our sufficient statistic, we're going to calculate optimal and approximately optimal policies. And then in the second stage of the experiment, we're going to experimentally implement these policies, and we're going to compare the actual performance that we estimate to what we predict based off of stage one. I'm not going to have time to talk about this today, but in sort of section 6 of the paper, we try and unpack the mechanisms that lead to the optimal policies we find. So things like how do behavioral biases impact performance? We'll try and characterize the mistakes that humans make. And we'll also ask how does an endogenous effort response impact the informativeness of the human's own information. So I'm going to introduce just a little bit of notation just to sort of fix our ideas. So there's going to be a binary state of the world, omega. This is whether or not a fact is true or false. Every case receives a classification A, and the designer is trying to maximize classification accuracy. This last point's actually not required for the framework. We could think about different preferences the designer may have, but this is going to be the empirically relevant set of preferences for our experiment. The designer is going to have access to an AI assessment. It's going to be calibrated, and they can choose to either follow the recommendation implied by the AI assessment, so they can automate a case, or they can delegate the case to the humans. And if they delegate the case to the humans, they get to pick a disclosure policy, which is just going to be a mapping from AI assessments to a distribution over possible signals that we could tell the human. So this is going to be the set R. In general, this could be quite a large set. So we could say, like, it's likely this case is true. We could also say there's a 70% chance this case is true. We're going to make an assumption on the next slide that's going to sort of simplify the space of signals that we have to consider. So just to recap, the designer's problem is to pick an automation and disclosure policy that's going to maximize the performance of the collaborative system. So here's sort of the main assumption we're going to make that allows us to get some traction on this problem. We're going to assume that human accuracy, when they see a signal R, is going to depend only on the posterior that this induces. So in particular, this is going to be the probability that omega is 1, so the share of true statements conditional on seeing a signal R, and we're going to call this X throughout. We'll call V of X the probability of a correct classification conditional on seeing or having a posterior being induced of X, and this is the sufficient statistic that we're going to need to estimate. There's a series of models under which this holds. We're not going to try and microfound this assumption. Rather, we're going to maintain it and then try and reject it empirically in stage 2. Just to give an example of what this assumption actually means, it means that the probability of a correct classification is going to be the same if the AI says there's a 60% chance that this case is, or that this statement is true, or if we say there's a 50-50 chance that the AI assessment is either 0.5 or 0.7, because both of these induce the same posterior. So this is a strong assumption, but it's actually quite powerful. It's going to allow us to, for any counterfactual automation or disclosure policy, to predict performance of that policy in a counterfactual sense. So for automation, it's actually pretty easy to predict performance because the AI is calibrated, so we know an expectation how it should perform. But for disclosure policies, this is a little trickier. What this assumption says is for any signal that we might want to tell a human, all we have to do is calculate the posterior this induces, and then we look up in the function v, evaluate it at this posterior, and this gives us our prediction for performance. So that's sort of the two slides of theory, and now we'll talk about the empirical results. So again, this is going to be a two-stage experiment. The first stage, the goal is to estimate V, and then use that as an input to calculate optimal and approximately optimal policies. The second stage, we want to actually implement these policies, compare the predicted performance to what we actually measure to try and validate this framework. As I alluded to, we're going to study a collaborative task where humans are checking the veracity of statements. We're going to use an established data set of politically neutral facts, so we don't think like motivated reasoning is really playing a role here. For every case delegated to the human, we're going to measure a continuous probability assessment. We'll automatically convert this to a binary classification on the screen. And it will also measure effort through a couple different measures, so things like whether or not they use external sources, as well as the time it takes them to actually check the fact. We're going to create an AI fact checker using GPT. So we're just going to ping the API and say true or false, pass the statement. We'll recover the distribution over next most likely tokens, and we're going to calibrate it ex post to our data set, so we don't have to worry about this assumption that the AI is in fact calibrated. We'll recruit our participants from Prolific, and they'll be incentivized. Sorry for those in the back, you can't see the bottom so well, but they're incentivized through a proper scoring rule. So it's in their best interest to report their true posterior belief about the likelihood that a statement is true. So now let's talk about some results. So again, before we get to the results, stage one, 1,500 participants. They each assess 30 statements with the AI fully disclosed to them, and then we're going to estimate V, or the sufficient statistic, using a kernel regression. So here's the estimate V we get. Just to explain this figure, the x-axis is showing the AI assessment, and the y-axis is showing the probability the human correctly classifies a statement conditional on the AI assessment. These 45-degree lines here, this is the performance implied by fully automating a case, and this follows from the fact that the AI is calibrated. A couple things to note. First, this function's convex. This implies that whenever we delegate a task to a human, it's going to be optimal to fully reveal the AI signal. So there's no benefit to withholding information in this setting, and this follows from Jensen's inequality. Second, we can immediately reject Bayesian updating. So a Bayesian with correct beliefs is going to do at least as well as automating the cases, because the humans have access to the AI assessment. So the fact that our sufficient statistic is below the 45-degree lines for certain signal realizations tells us that our humans are not Bayesian updaters. Finally, the same sort of fact implies that there's going to be a benefit of automating some cases, particularly cases where the AI is confident. So the AI assessment is close to 0 or close to 1. So now we'll talk about the optimal and approximately optimal policies we're going to consider. We'll consider two classes of policies. The first is where full automation is allowed, and then we're also going to consider a class of policies where we don't allow for full automation and where the human has to make the final decision. So if automation is allowed, the optimal policy is going to be full disclosure plus automation. So we're going to automate cases where the AI is quite confident. The remaining cases we're going to delegate to human decision makers, and for all cases we delegate, we're going to fully reveal the AI assessment to the human decision makers. The optimal policy when automation is not allowed is just going to be full disclosure. Okay, and this is because that V curve is convex. We're going to consider two approximately optimal policies, and we're going to do this for two reasons. First, we think it's kind of interesting that these sort of simple disclosure policies are, in fact, approximately optimal. But second, they're going to give us a way to directly test this assumption I made a couple slides ago. And that's because they involve a non-trivial disclosure policy. And I'll sort of explain that test a little bit more carefully in a few slides. So the no disclosure plus automation policy is where we automate cases where the AI is confident, and the cases we delegate to the humans, we don't tell them anything about the AI assessment. Stoplight just restricts ourselves to revealing 3 signals, so you can think of like likely false, uncertain, likely true. And then we're going to have a baseline of no disclosure plus no automation. We can generate numerical predictions for all these policies. In the interest of time, I'm just going to skip to some qualitative predictions. The first is that automation is valuable. So the optimal policy with automation is preferred to the optimal policy without automation. Second is that human information is also valuable. So the optimal policy outperforms the policy of fully automating every single case. Third, we're going to find that direct human-AI collaboration is valuable, but it's only valuable when automation is infeasible. And we see this by the result that the optimal policy without automation, full disclosure plus no automation, outperforms the sort of benchmark of no disclosure plus no automation. But when automation is allowed, we actually find that direct human-AI collaboration is not so valuable. So full disclosure plus automation is approximately the same as no disclosure plus automation, and then the other sort of approximately optimal policy is in fact approximately optimal. Okay, so let's talk about the second stage. So remember, we have 2,000 participants. It's a within experiment, so they're each assessing statements under all 5 policies. And here I'm going to plot for every policy the predicted performance from both stage 1 estimate of V as well as a stage 2 estimate of V against the actual estimated performance in our data. So first we have our benchmark of no disclosure plus no automation. This is in fact the worst policy as we predict. And I'll highlight that this is actually sort of the biggest miss in terms of how our framework does at predicting performance of all the policies. And this is for sort of subtle reasons that I'm happy to talk about during the reception. I won't go into it now in the interest of time. If we think about the policies where automation is not allowed, we find that the optimal policy, full disclosure plus no automation, improves over this benchmark as we predict. And stoplight, an approximately optimal policy, is in fact approximately optimal. We can't reject that the performance of these 2 policies is the same. If we move on to policies where automation is allowed, again, we further improve performance. And again, these sort of qualitative predictions are borne out. The approximately optimal policy is, again, approximately optimal. So the key takeaway here is that, first, it's valuable to optimally design human-AI collaboration. We substantially increase performance in the optimal policy relative to sort of naive benchmarks. And second, these sort of qualitative predictions are borne out in our data, which gives us some confidence that this framework is a useful guide to designing policy. However, we can actually test this assumption I made at the outset pretty directly using these approximately optimal policies with a non-trivial disclosure policy. So here I'm again plotting V, but for the policies that involve non-trivial disclosure policies, I'm also plotting performance conditional on the signal that we show them. So for stoplight, we send 3 different signals. These induce 3 different posteriors, and we can test this assumption if the actual performance at these we can test the assumption that the actual performance at the posteriors we induce is equal to what we would predict. And we see that in all cases we're pretty close to this blue line, which is consistent with this assumption holding. So we feel pretty comfortable that this assumption is a reasonable approximation to the data, at least in this setting. So in the interest of time, I'm going to skip this recap because I'm going to recap in 2 slides, and I'm just going to spend 1 slide talking about mechanisms. That 1 minute. Okay, great. So in section 6, we try and unpack the mechanisms a little bit. So we first, in sort of an assumption-free way, try and put a bound on the share of incorrect classifications that humans make that are due to non-Bayesian belief update. And we find that about 8%, or at least 8%, of incorrect classifications are due to these non-Bayesian update. We then try and characterize the type of mistakes that humans make. So we introduce a definition of over and under response to new information, and then we decompose the under response to the AI signal, which we see because that V lies below the 45-degree lines, into overconfidence and AI neglect. We find it's almost entirely due to overconfidence. So humans act as if their own information that they get from Googling or whatever is more accurate than it actually is. Finally, we ask, how does the endogenous effort response that we observe in the data impact the informativeness of the human information? And so, in particular, we find that when humans see a confident AI assessment, they, perhaps rationally exert less effort. And so we try and ask, does this lead to their own information being less accurate on those cases? We find only modest evidence of this effect. So now I'll just wrap up. The purpose of this paper is to introduce a framework that allows us to tractably solve for optimal disclosure and automation policies. The methodological takeaways, in my view, are that the sufficient statistic approach seems to work at predicting treatment effects, and it allows us to design an optimal policy. On the substantive front, pretty much all these qualitative predictions that I outlined are borne out. So full disclosure is optimal. There's a lot of gains from automating cases where the AI is confident. This happens because humans are overconfident in their own information. The value of direct human-AI collaboration is modest. And then I didn't get to talk about this too much, but we actually find that the optimal design corrects for the mistakes that humans make in their biased belief. So thanks for the time. Happy to answer any questions.